All right, let's do, given a state space, find the transfer function and find the state transition matrix. State space given here, I'm going to put the labels on it so it's easy for us. Here's A, here's B, here's C, and there would be a D here, but there's no D matrix in this one. So okay, we know our A, B, and C matrices from the given state space. Find the transfer function. Okay, transfer function is going to be called H of S. It's going to be equal to C times S I minus A inverse times B plus D. D's not part of the equation, so it's not right. Okay, let's just write it out. C is 1, 1. Si minus A is S 0, 0, S minus 2, 0, 0, 0. And we'll be needing the inverse of that times B, which is 2, 2. Okay, I'm going to go ahead and call what's inside of here. I'm going to call it M. So M is equal to S minus 2, 0, 0, and S minus 0 are just S. That's M. But I need M inverse, so first step of the inverse, let's solve for the determinant of M is going to be these ones multiplied together minus those ones. So it's going to be S times S minus 2 minus 0. So the determinant is just S times S minus 2. And now to solve for M inverse, I'm going to do 1 over the determinant, which is S minus 2 times the adjunct of this. So we're going to flip the diagonal entry. So it's going to be S minus 2, 0, 0. And now we can also write this as S 0, 0, S minus 2 divided by S times S minus 2. Okay, so we have our M inverse, and that's the real meat and potatoes of this formula here. So let's clean this up. We have M inverse, and it is S 0, S minus 2, 0, divided by S times S minus 2. And B is still 2 and 2. All right. Oh, we can get rid of this. Let's keep this clean. All right, and we'll go right to left when we're doing matrix multiplication. Let's do our 2 by 2 right here times a 2 by 1, which is going to leave us with a 2 by 1. All right, let's do it. Oh, and it's all going to be divided by S minus 2. 2S plus 0S, S times 2 is 2S, plus 0 times 2 is 0, so 2S. 0 times 2 is 0. S minus 2 times 2 is 2S minus 2. Okay? Big brackets for there, and now we're going to multiply that by our 1, 1 right here. here, and that 1, 1 is going to be a 1 by 2 times a 2 by 1. It's going to leave us with a 1 by 1. Okay. 1 times 2s is 2s, plus 1 times 2 times s plus 2 is 2 times s, not s plus 2, s minus 2. And that was all divided by s times s minus 2. Okay. Let's bring that up. That's a decent final result, but we're going to clean it up. So, took care of all of this. Took care of all of that. Let's just bring this up. Don't get it twisted. When I was doing the numerator denominator thing in the previous operations, remember I was doing it underneath the matrix, as if to say I'm going to element-wise divide everything in the matrix by alpha. This expression is one expression, numerator denominator, so that was this. Let's clean that up, and now let's clean this up. 2s plus 2s minus 4 divided by s times s minus 2. All right, let's clean that up. 2s plus 2s is 4s minus 4 divided by s times s minus 2. All right, let's clean that up. 4 times s minus 1 divided by s times s minus 2. Final answer. Here's your transfer function. Right here. H of s. Now, recall this as well. Remember, your transfer function is always your in, as I was. Transfer function is your output divided by your input, which is usually your output will be y of s over input of r of s. So y of s is equal to this top expression, r of s equal to the bottom expression. So you're going to have 1, 0, and 2 poles. But nevertheless, transfer function solved. Next, we're going to find the state transition matrix. Okay. What you do to find the transfer function from a state space can be helpful, but we're just going to do it from scratch here. The state transition matrix is a matrix called phi of t, which is also equal to e to the at, which is also equal to the inverse Laplace of phi of s. Phi of s is going to be equal to si minus a inverse. So to be written out in terms that we can work with, final general setup, phi of t, which is what we want, is equal to the inverse Laplace of si minus a inverse. We just solved for si minus a inverse here, but again, we're going to do it from scratch. So we're going to call this n, capital N. N equal to Si minus A, which is equal to S 0, 0, S minus A 2, 0, 0, 0, which is equal to S minus 2, 0, 0, S. M is right there as I was, N right there, and we need N inverse. The determinant here is going to be S minus 2 minus 0. So we're going to have our adjunct matrix where we swap S minus 2, 0, 0, divided by S minus 2. So what I was saying before, remember I had these 4 elements in this 2 by 2 matrix. Now I'm going to element-wise divide each of them by this expression down here. So notice before we didn't simplify, we didn't reduce anything, we didn't cancel terms, we weren't trying to reduce our ability to objectively see the states in the system. But here we can for the state transition matrix. So let's write this out big. It's going to be S over S minus 2. 0 over that would leave 0. 0 over that would leave 0. And this is going to be S minus 2 divided by S minus 2. So the S's will cancel, S minus 2's will cancel, and we'll be left with 1 over S minus 2, 0, 0, 1 over S. So N, which was our Si minus A, was what is here? S minus 2 and S. N became S minus 2, S, 0, 0. And N inverse became one over those things. Here's a fun trick about matrix inverses. If you're dealing with a purely diagonal matrix, something like Q equal to A, 0, 0, B, and you want Q inverse, and you have this purely diagonal matrix, you can just do 1 over A, 1 over B, 0, 0, real quick. But like I said, we're doing this one from scratch, so we did the whole thing. Either way, we wind up in the same place. That would apply to this because we're dealing with a purely diagonal matrix, but we did it from scratch, so we arrived here. So now let's expand out on our formula. This whole thing inside of these squiggly brackets is N inverse, which is right here. So this is telling me that I need the inverse Laplace of a matrix that is 1 over S minus 2, 0, 0, 1 over S. We can get rid of this. We know N inverse, we know N. We don't need N anymore. Here's where we're at. The Laplace transform of this 2 by 2 matrix is simply an element-wise inverse Laplace transform. Sorry. The inverse Laplace transform of this 2 by 2 matrix is really just an inverse Laplace transform of each of the elements in it. So those are going to be 1 over S minus 2 is going to leave us e to the 2t, 0 gives us 0, 0 gives us 0, 1 over S gives us 1. Therefore, state transition matrix phi of t equal to e to the at equal to the inverse Laplace transform of phi s, where phi s is equal to the inverse of Si minus A. We called Si minus A n. We solved for the inverse of n, and now we're taking the inverse Laplace transform. We wind up here saying that our state transition matrix, e to the at, is equal to e to the 2t, 0, 0, 1. There's your state transition matrix.